Hi everyone. Today we're going to be talking about minerals. Introducing minerals before we start talking about the rock cycle. So for this section of the class, we are going to be learning to describe and define minerals and also how minerals can form. And then looking at how geologists organize minerals, because there are quite a few to keep straight, as well as determining the most common minerals and then actually identifying minerals based on their different properties. So to start, what's a mineral? A mineral is the building block of all rocks. So all of our developed societies actually really depend on minerals. So both metals being copper, lead, aluminum, iron, and non-metals, quartz, gypsum, feldspars, limestones. Minerals are very economically important as well as historically important. For example, here I have malachite showing you here and gold. We know gold has definitely been important both historically and economically. So minerals, the definition of a mineral, so in order to be considered a mineral, it must be naturally occurring, which means it grows in nature. It must be a solid that can maintain its state. It must be a crystalline material, which means that the atoms of the mineral are locked in place by chemical bonds, so they have a very specific order or structure to the atoms. They must also have a definable chemical composition, which means there is a chemical formula that exists for that mineral. So we know exactly what is in each mineral. And the last is it must be inorganic. This one's a little iffy. Almost all minerals are not organic or inorganic, meaning that they do not form from living organisms. But more recently, we have added some minerals to the definition that actually are organic minerals. We'll get into that when I start talking about how minerals form. There is one way that minerals can form organically. But for the most part, minerals must be grown naturally, a solid with a defined chemical structure, and it must have a defined chemical composition. So for example here, if you were to look at these three objects, we have ice, mercury, and sugar. And I said, which of these is a mineral? We would say, let's start from the bottom. Mercury is a liquid, so it is not a mineral because it is not a solid. Sugar is organic, so it's made from organic material. So sugar is not it is not inorganic, meaning that that does not fit our definition of a mineral. Ice, however, does. So ice actually fits our definition of a mineral, funny enough. So when we start talking about minerals, we start talking about rocks. So rocks are made from minerals. So all rocks are made up of a combination of minerals. So most rocks contain more than one type of mineral combined. So for example, this is granite. Kind of looks like a countertop you might have seen in a kitchen. This is actually feldspar and quartz and hornblende that have all grown together. So you'll see that you can see sort of pink specks, that's the potassium feldspar. The white shiny specks is quartz, and then the dark black is hornblende. So that's a common combination in granite. So there are some rocks that are made up of only one type of mineral, but it's much more rare. So salt, limestone, those are some examples that have only one mineral in them. Most rocks have a combination of multiple minerals that have all grown together to create that rock. So I mentioned that minerals must have a crystalline structure, so I wanted to get into a little bit more of what that means. It means that the atoms in the mineral are in a very specific order. So for example, this would be a crystalline structure. It's based on the pattern of the atoms. So a solid that does not have a crystalline structure, such as this up here, is called a glass. So it's a glass. Obsidian, for example, this mineral here, does not have a crystalline structure, so it is technically a glass. This mineral, whichever this would be in my little cartoon, this would be something that has a crystalline structure. So our crystals, so minerals grow in crystals. So a crystal would be a single continuous piece of that mineral. So it's growing naturally in a very specific shape due to whichever mineral it is. So the atoms in your crystal are going to be very specifically ordered, and all minerals form crystals. So for example, here I have two atomic structures. Which of these would be the structure of a crystal? The answer would be this one, because it has a very specific order. This here would possibly be the atomic structure of something like a glass. So crystals can be in many different shapes. So depending on what type of mineral you're looking at, that's going to dictate which type of shape the crystal grows in. So minerals have faces. So the faces of a mineral are the sides. Minerals grow best in an open space, so where the mineral can grow in its own shape. We have different mineral examples down here at the bottom showing some of the different shapes that crystals can grow in. So we call the pattern of the atoms within the crystal lattice. So the pattern of the atoms, or what we call the crystal lattice, is essentially what controls the shape that the crystal is going to grow in, or the crystal structure. So for example, halite, which is salt, grows in a perfect cube all the time. So halite will always grow in a cube as long as it can. So the crystal lattice, this is the 3D shape that the crystal will actually take, and it depends on the order of the atoms. So here is galena, and here is halite. So we can see they are both cubic. So they grow naturally in nature in this perfect cube shape. This is one of my favorite minerals here. And salt as well grows in this perfect cube shape. So that shape is due to the crystal lattice, or the pattern of the atoms. So that pattern is just repeated over and over in these 3 dimensions. So I mentioned that crystals grow best in an open shape, in an open space, excuse me. They can also grow together, like we saw in the example of granite earlier. So teeny tiny little bits of crystal act like a seed for further crystal growth. So over time, crystals grow outward from that center seed. So the crystal is going to grow outward from the center, but it's always going to maintain its same orientation, its same shape, until it can't anymore. So the shape that the crystal grows in depends on the internal atomic structure, and the crystal and minerals will grow to fill up all the available space. So over time, you'll notice in this diagram here, these crystals are going to bonk into each other. They're going to grow to the point where they hit each other. At that point, the crystals will stop growing along the sides where they've hit each other. They will continue to grow outwards where there is available space. So this is how we end up with crystals or minerals that are not in their perfect crystal lattice, in their perfect shape. It's because there is not enough room. So the mineral will continue growing outwards in this direction, but it, of course, will not continue growing towards the other minerals because there isn't space. The mineral will grow and fill up all of the available space until it runs out of material. So I have some videos to show you in a second of minerals growing. So Essentially, when minerals have open space, great crystal faces grow where you can actually see the shape of the crystal and how it grows naturally. When crystals are in a confined space, we will not see the crystal faces, so we don't see that naturally occurring shape because it just grows as much as it can. So here you'll notice that those crystals are growing. They're about to hit each other. And then this crystal, the top middle, more red crystal, will stop growing in that perfect shape once it hits something else. So this is under a microscope, I should mention that. So the crystal continues to grow outwards where it can, but where they have combined, where they've met, the crystals stop growing in that direction. So here's another example. This is salt. So this is halite, which grows cubic. So you'll see that salt crystal in the top of the screen growing as a cube. You'll see there's a few more that start to grow. Ignore that pop-up there. So they grow in these really cool, naturally perfect cube shapes. So that is salt, which we call halite. So now that we understand how crystals themselves grow, let's talk about how the mineral begins to grow in the first place. So we know that each crystal is going to grow from the inside out, and it's going to continue expanding until it cannot anymore. So let's talk about the different ways we can actually, in nature, grow minerals. So this is a diagram that shows all the different ways. I'm going to go through each and explain them. So the first way to grow a mineral is through solidification. So we're going to talk about this a lot next week when we talk about igneous rocks. Solidification is when minerals grow from a liquid molten rock, so either lava or magma. Lava being when it's on the surface, magma being when it is under the surface of the earth. So solidification occurs as that molten rock is cooling and solidifying into rock. So as the molten lava cools, those minerals are going to be able to form from the material in that molten lava. So you'll see this figure here. Here we have a completely molten rock, and then over some time it cools and we have certain minerals that start to form. The minerals that form depend on the temperature as well as the material that makes up this magma. So that's going to dictate which minerals can form. And then as it cools even more minerals will form. These minerals will get larger as they're growing until the rock is completely solidified. So we also have precipitation. There's actually two types. So this is precipitation from a liquid. So precipitation of minerals occur when we have, let's say, a body of water. That water evaporates, and then all of the minerals that were in that water will actually be left behind. So for example, we can talk about salt with the ocean. As the water evaporates, the salt does not evaporate. That salt is actually going to be left behind. So the water then becomes super saturated. It gets to a point where the water, there's too much water removed. There's not enough water left behind to dissolve that salt. There's too much salt in the water. The salt is actually going to solidify out. So the salt will become a solid salt instead of dissolved in the water, and it will fall to the bottom. This is how we form salt flats and how we can get salt from our ocean water. There's also what we call precipitation from volcanic gas. So there's a lot of elements, there's a lot of nutrients in volcanic gas. So similarly to how we can precipitate out of water, minerals can also precipitate out of volcanic gas. So this often happens with sulfur, which is released in large amounts from volcanic eruptions. So as that volcanic gas travels over the surface of the earth, we will see that that sulfur is actually going to solidify out on all sorts of surfaces. So you'll see here, this yellow is the sulfur completely covering these surfaces. Next we have diffusion. So diffusion happens within solid rock. So this happens incredibly slowly. So diffusion is where we have a solid rock that already exists, and over time, a very, very, very large amount of time, the atoms within the rock will actually move and migrate together to form new minerals. So there are certain minerals that can form within a solid rock just due to time. So garnet is an example of a rock that commonly forms through diffusion. So these are garnets here within this schist, which is a type of rock. So the garnets actually grow within this rock over time, because over time the atoms actually shift around within the rock. And then the last way to grow a mineral is what I was talking about a little bit earlier. It's called biomineralization. So this is where more of a new concept for minerals. We actually have minerals created by organic organisms. So there are certain minerals that we do now consider minerals by definition that are produced by organic organisms, often in the ocean. So organisms that produce shells, for example, or organisms that live around a reef, often actually extract ions from the water to create their shells. So those shells we can consider a mineral. So this is where there are only certain minerals that actually are created by organic organisms. So here's a summary page of the different ways to grow a mineral: precipitation from water, precipitation from gas, diffusion, biomineralization, and then solidification from a melt. We're going to talk a lot about solidification from a melt in this class in the next few weeks. So as minerals grow, they can either grow uninterrupted, which we discussed. This is where we can have very clear crystal faces. We can really easily see the shape of the mineral. For example, here, it had an uninterrupted growth, so these minerals could grow in their preferred structure. We can also have interrupted growth. So this is where we have anhedral crystals, which means that the crystals do not grow in their preferred shape. They just grow to fill up space. So they fill up as much space as possible around the other obstacles, which are generally other crystals. So now that we know how minerals are created, let's quickly go over how minerals can be destroyed. So the most common way is through melting. So this is where we heat the mineral to the point where the chemical bonds physically break apart. You are completely destroying the mineral. There's also dissolution. So this is the opposite of how water can help form minerals. They can also destroy minerals. So water or another solution will actually separate the atoms within the mineral or within the crystal. So water can actually dissolve that mineral and separate the ions in the atoms within the mineral, essentially destroying that mineral. There are also certain chemical reactions that can cause destruction. So there are certain minerals that are reactive. So these chemical reactions will destroy the mineral as well. And then there are certain microbes that consume different minerals that through that will also destroy the minerals. The most common and the two that we will talk about the most in this class are going to be melting and dissolution.